Hello, good afternoon, and welcome everyone, and thank you for joining us for this webinar, Heterogeneous Integration in Action, Powering the Next Era of Connectivity. I'm Ilan Englard, EU Project Manager and Consultant, and I have the privilege of serving as the coordinator for HiCONNECTS on behalf of NXP. Today I will open our session, set the next context, and then introduce our distinguished speakers. Over the next 2 hours, we will explore how heterogeneous integration is enabling Europe to push the boundaries of connectivity, bridging cloud-to-edge system, advancing 5G, 6G, and cultivating energy-efficient architecture for IoT and artificial intelligence. HiConnects, comprised of more than 60 partners across Europe and funded by ChipJU, is at the front end of these efforts, integrating innovation in packaging, materials, and architecture design to accelerate industrial uptake. Connectivity is the lifeblood of our digital age, whether in smart mobility, data centers, consumer electronics, or edge devices. The demands on performance, energy, miniaturization, and flexibility keep growing. Heterogeneous integration offers a path to meet those demands by enabling these similar technologies, for example, chips, sensors, RF, photonics, advanced packaging, to work in concert more seamlessly than ever before. Today's program will spotlight key technical achievements from across the HiConnect consortium, uncover lesson learned, and look ahead to how this innovation can be adapted across Europe's semiconductor value chain. Before we get started with our first presentation, I'd like to introduce our speakers, each of whom bring a unique perspective from across the research, design, manufacturing, and application domains. First, we have Daniele Pagano, project manager at ST Microelectronics. Daniele brings years of experience in wafer fab operation and collaborative EU projects, such as Improve, Integrate, Made in 4, and Saturn, and will share insight from HiConnect's technical progress in process integration. Next, we have Hussein Yurdakul, who leads the Autonomous Mobile Robot System Software Center of Excellence at BluePath Robotics. Hussein will speak to how heterogeneous integration plays into robotics, automation, and next-generation system-level architecture. Following Hussein is Julio Ortiz, a senior software product marketing manager at Thermo Fisher Scientific. Julio has a rich background in electron microscopy, and he will connect the dots between cutting-edge characterization, integration technologies, and system-level performance. Then we'll hear from Tolga Budrumulu, lead autonomous driving development engineer at AVL Turkey. Tolga works across perception, sensor fusion, and intelligent systems, and will address how heterogeneous integration enables next-generation automotive and mobility applications. After these talks, we'll open the floor for a question and answer session. So please save your question and use the chat or Q&A panel to submit them. So without further delay, let me hand over to Daniele Pagano to begin the presentation. Daniele, over to you.
Good afternoon. I am Daniele Pagano, Project Manager at ST Electronics. Today, I would like to share with you some results for manufacturing of power device in the next year of connectivity. Few words about myself. I have a master degree in physics. I have joined the ST Electronics in 1999. I spent my experience always in front end. I cover the different role and position, and currently I am project manager for founded project, maintenance program, and cybersecurity. Today, I have the pleasure to describe the improvement, the activity that we are developing in manufacturing in the framework of the project HiConnect. And at the end of presentation, some takeaway to remember what we discussed now together. Regarding the project HiCONNECT, consider that is founded by ChipJU, is composed by 67 partners coming from 15 countries. The main objectives are developing heterogeneous integration for energy efficient and high performance wireless wired cloud and edge computing, as well as automotive radar, in order to improve transmission of Internet of Things, data over IP network, and sensing of objects to enable highly automated driving. Consider that also we have other development that are focused on RF technology, radar, IT data, infrastructure, but focus the attention of heterogeneous integration object. We talk regarding a system composed by different components, so is easy to understand as the failure of only one component brings to the failure of the system. For this reason, work on improvement the quality in manufacturing have a result and an impact directly on heterogeneous integration system. So I want to share with you only few slides regarding our company, ST Microelectronics, because the market that we serve, the product that we develop, are really a sort of enable for the system that we want to improve the performance. Consider that our company has exert in Europe, in between from France and Italy, but we have also some plant in Sweden, in Morocco, Malta, Singapore, Malaysia, China, and Philippines. We talk more than 15 fab. In our strategy, we cover smart mobility, power and energy, cloud connected, and autonomous things. Furthermore, we address four end markets like automotive, industrial, personal electronic, communication equipment, computer, and peripherals. But we have also to consider which type of product we develop to cover this market, and they represent the key to enhance the performance in heterogeneous integration. Consider that we develop smart power BCD, power MOSFET, IGBT, silicon carbide, gallium nitride, and RF product, MEMS, and in general in Italy we produce a big part of analog device uh, sold by our company. At this point, is important to define what we are going to improve in our factory. We analyze three main tasks. One related to Industry 4.0 and IoT. The second was focused on process and equipment performance optimization for yield improvement. And the third one is to contribute to develop a modular approach in order to include different data silos different information in order to cover the full line in principle from design to the backend. You can see also a lot of partners with we are collaborating tightly in this project. Regarding Industry 4.0, consider that in our factory uh, is really important to optimize the dispatching for each equipment of lots that we have to produce. Because the characteristic of our factory is that we can describe them as high mix, low volume manufacturing environment because we have several technology with low volume of product that we produce. So, in general, the production of semiconductor device is really complicated, but in this case, a little bit more. Our challenging target was set as 10% in terms of productivity, and we are collaborating with the University of Catania and Polytechnic of Milano. Polytechnic of Milano is covering an holistic approach in order to describe all factory, and the University of Catania is the major focus is on critical step in between from cleaning and diffusion process. This is a typical problem because it's necessary to optimize and maximize the number of moves so of the processed wafer, avoid also scrap and rework, obviously. But taking account that, as said before, we have a line that produce high mix low volume. So we have different technology, different product. Sometimes they have to perform only the cleaning. In other case, cleaning plus diffusion. And other product need an additional diffusion step, the second diffusion step. So furthermore, it's important to take in account that we have to mandatory maintain the duration of the transition from cleaning to diffusion to the other work area, a specific time range. So this important constraint we must be guaranteed. Otherwise, there is a risk of scrap in the worst case, or at least a rework of the lots. Consider that in this preliminary phase, the University of Catania uh, obtained relevant results. In fact, we obtain an improvement in terms of productivity around 5%. Consider that this is result is really significant for us, and we are confident that by the end of the project, in September next year, we will achieve the results and the KPI that we defined at the beginning of the project. When we talk regarding digital twin and to find a way to reproduce at least some part of the process, is really important to have all the crucial information that can help us to understand and anticipate potential drift or problem in the line. So, a important topic is related to the usage of sensor that we can modify in some way, transform as smart sensor, and I mean that it is a way to collect the information and include the results in the internal network. In this case, our colleague in Agrate are working on sensor that are present in subfab. We are talking about pump, abutment system, and so on. And another challenge is represented by the position, the location of this sensor, because usually are inside the bunker, so not easy to connect or put inside a connection. In this case, Corretigo developed and overcome several challenges to connect this sensor to the network. Also, Politecnico worked to develop the graphical user interface. In this case, we are in the phase of deployment in the fab and are really confident to complete rapidly this task. Another important topic is represented by equipment performance optimization. In this case, the object is correlate electrical performance with inline process and metrology parameter in order to speed up the root cause identification and anticipate potential deviation in terms of final performance. Uh, is a complicated task because it's necessary combine uh, in electrical wafer sort all data, really big data, that are related to all wafer for all die present inside the wafer, and what we obtain following our process control plan in line when we perform metrology measurement to take under control the process. In this case, we analyze also a sample wafer for each lot and only some die inside the wafer. So, in this case, we are working with the University of Catania, Siemens CDA, and IMT. And as showed before, is really important to improve the metrology part. So to have new machine to perform measurement without scrap wafer. In this way, it's possible to perform inline measurement directly on production lots. For this reason, we are working tightly with some metrology partners. In this case, I talk regarding Semilab, Bruker, Nova, TNO, UPB, and also recently NFI. The scope is always for new material and new approach. So, for example, with Semilab, we are exploring a new method so in order to obtain a characterization of the silicon carbide bulk using approach that are standard in silicon. But obviously, we talk with a different material, and the situation is totally different. Also, for this reason, really important. When we talk regarding silicon carbide, an important topic is represented by the effectiveness. So, with Bruker, we are analyzing the opportunity to use high-resolution X-ray imaging in order to perform and replace a destructive trial. And in similar way, we are working with NOVA, TNO, and UPB. These represent the future for also next development and a way to make more robust the algorithm that other partners are developing now. In, in order to take also under control the process, our colleague Negrate focused the attention on the dry edge process step. Consider that when we introduce a new product and typically we have different process flow, different material, the standard advanced process control APC sometime is no more capable to catch equipment drift. So the work, in this case, they first added new sensor, in this case, optical emission spectroscopy, and a new algorithm developed by Politecnico di Torino in collaboration with Orsa Group for the software solution. Also, in this case, we have to face unbalanced dataset. That is the typical situation in the semiconductor environment, because also in this case, we have a lot of wafer in the best condition and only few that have better performance. So also from this point of view, it's not easy to find the right algorithm, but thanks to our partner, now we are in the condition to deploy this new approach directly in production and start to gain the benefit of this collaboration. The last step is to give our contribution. So you can see that partner of Siemens and MIT are some semiconductor manufacturing and also metrology partner in order to develop a modular approach to cover all the line and include in easy way new information when is necessary. For example, we introduce a new machine, a new data silos, and thanks to the work developed by Siemens, it's possible to reduce drastically the time needed to include new data, new source of information. To summarize what Siemens NDA and MIT are developing for us, the next slide can help me to describe the topic. You can see a representation of front end. We have the front end of line and the back end and the electrical swap. So when we talk regarding the front end, we have a statistical approach to decide which wafer to be measured for a specific process step. So you can see the green wafer that give you an idea that with different rule in different process step, we select a certain number of wafers and a certain number of sites in which perform the measurement. Instead, at a EWS measurement, we have all the information, all wafer measured, all devices. So this is the first difficulties that they have to face, but was really successful because they uh, find a way to uh, pay attention on correlation that we can confirm as physical correlation among electrical data and inline measurement. The first KPI was achieved. For us, it's really important to speed up the time needed to identify the root cause of a problem. In this way, when we have a problem on specific electrical parameter, it's possible to identify a few process steps that can contribute. But in order to improve more the approach, after this step, when we have a process of electrical measurement of instance, is possible to introduce a, FDC, fault detection classification data, in order to improve the quality of the information. So it's possible to move from an average analysis, because we analyze at lot level, to wafer level. Is really important. And the next slide show you as is possible to take under control and verify correlation in terms of process step or electrical parameter. In this case, you can see process step and EWS parameter, and highlighted in red the correlation. So it's possible to understand for each electrical parameter which is the process step that gives the most important contribution. So it's easy to understand the process step that contributed to the failure, speed up the analysis, understand the problem, and anticipate potential drift. Is really an important result. So we are at the end of this little journey to describe you what we are doing thanks to Chips JU in the project ICONNECT. Consider that the focus is on heterogeneous integration, but is really important the contribution of semiconductor manufacturing. In conclusion, all the activity that we perform to improve the quality, the yield, the performance of device in semiconductor manufacturing have a great impact to enhance process of heterogeneous integration of power device. This is the key message from my side today. Now it's time for some knowledge and go on describing the main partner that we are collaborating, and they allow us to uh, achieve this type of important results. But once again, I want thanks the project ICONNECT that allow us to put the consortium and also to achieve this type of results. Thanks a lot and good afternoon.
Hello everyone, my name is Hüseyin Yurdakul and I am responsible for the system and software development at Bluepath Robotics. I am currently working on the HiCONNECTS project, specifically focusing on the smart logistic use case. Today, I would like to share our latest advancements in this heterogeneous integration use case, smart logistics and manufacturing, and the autonomous mobile robots. The first chapter will explore smart logistics and manufacturing, which constitutes our use case in the HiCONNECTS project. In the second chapter, I will provide a detailed summary of various types of autonomous mobile robots. In this use case, we are demonstrating fully autonomous smart automotive logistics and manufacturing. The modules integrated into the HiCONNECTS demo include heterogeneous components such as LiDAR and camera systems for sensing, a 5G network communication layer, AMRs, and a collaborative AI layer for the AMRs. In the use case, there are 14 partners from 4 different countries. Allow me to introduce them. NXP, Coretigo, Smart Universal, Turkcell, Securrail, Berlinator, TÜBİTAK, Bluepath Robotics, Ford Otosan, ITML, ULAK, and Harikopio University. The concepts and outcomes contributed by our partners. The first segment pertains to robots and hardware. In the use case area, the 5G infrastructure is provided by ULAK and Turkcell, with the 5G modem developed by ULAK. And TÜBİTAK has developed the secure IoT chip and LiDAR, while Coretigo has contributed the wireless IO link modules. And we are utilizing 2 different autonomous mobile robots, one developed by NXP and the other by Bluepath Robotics. The smart logistic operation is executed by Bluepath Robotics U2000 under dry differential model AMR. You can see the picture on the left side, left-hand side. And the second segment of our concept and output pertains to artificial intelligence and software. Our primary goal here is to management of task and traffic management through the support of end-to-end collaborative AI. The central coordinator application serves as the central control and monitoring system provided by TÜBİTAK, and social AI is responsible for managing traffic, providing by Berlinator, and the order manager acts as a middleware connecting the central coordinator with production planning. It comes from ITML. Additionally, order AI analytics predicts subsequent orders and shares this information with the order manager application. Also comes from Harikopio University. The technical specifications of demonstration AMR U2000 are as follows. Its maximum payload is 2,000 kilograms and maximum speed is 1.3 meters per second. Visual SLAM navigation is used, plus minus 1 centimeter position accuracy. When it is loaded in the demonstration, its height almost 3 meters and its weight is 450 kilograms. In the picture, you are seeing the demonstration area picture, which is loaded AMR with the parts, and use case area is located in Fort Otosan welding area. Fort Otosan Kocaeli plant is the only Ford plant is the World Economic Forum's global lighthouse network, recognized for its exemplary technological integration. The designated use case area is the body site right line within the welding area. This line necessitates the coordination of 14 distinct parts, facilitated by 3 loading stations and 10 unloading stations. You can see the layout of the area. It is covering wide area. Task and traffic management system encompasses 5 primary components. The central coordinator software oversees the monitoring system, while the order manager is responsible for resource management. Collaborative social AI manages incoming tasks and schedules. Peripheral system interface with automated gates and stations. Lastly, the AMRs are governed by the comprehensive task and traffic management system. Additionally, the agent applications integrated within the AMR's robotic software, including the TMS agent, collaborative social AI agent, and peripheral agent. The communication relies on the MQTT protocol. It is a lightweight publish-subscribe messaging protocol and with VDA 5050 interface. VDA 5050, developed by the German Association of the Automotive Industry and the German Engineering Federation. It is standardized communication interface designed to ensure interoperability between various automated guided vehicles, AGVs, and mobile robots from different manufacturers and the central master control system. Robotics supports VDA 5050, and in this project, we aim to provide outputs that are broadly compatible with other AMRs as well. The task and traffic management system incorporates heterogeneous communication and operations between edge and the central system. Local server communication and cloud-based modules interact seamlessly, providing input and output for their respective applications. Communication with AMRs is facilitated via an MQTT broker. Within AMRs, internal communication is enabled through ROS topics, ensuring real-time coordination. The AMR operation protocol adheres to VDA 5050 standards. Peripheral connectivity is achieved by integrating production line devices such as gates and PLCs through IO-Link wireless bridges, ensuring flexible and scalable connections. The central coordinator software offers a user interface accessible via both mobile and desktop devices. You can see the simulation of the demonstration area. Relenators social AI effectively prevent deadlock between 2 AMRs in a one-way narrow path application. The AMRs communicate and decide on the optimal course of action before entering the narrow path. In the unloading area, you can see one AMR leaving the pad to allow an AMR with a full order to pass. In conclusion, the management system for secure, connected, autonomous mobile robots incorporates high dynamic range LiDAR sensors and AI-supported task and traffic management at the edge. And in the second chapter, I will introduce the autonomous mobile robots developed by BluePath Robotics. There are three primary product families are underdrive, towing, and forklift. Type AMRs are designed to transport containers and trucks using lifts. These are also have functions as process AMRs. They are providing a versatile mobile platform that facilitates the creation of dynamic and flexible production lines. It is next generation production lines. And second type is tow type AMRs are designed to pull carts with automatic mounting mechanisms. These are two vertices, one with a pin mounted from the bottom and other that pulls from the rear. These AMRs come in various capacities ranging from 2,000 kilograms to 20,000 kilograms in three categories: low, medium, and high. You can see on the screen. And last one is forklift type AMRs are designed to pick up, transport, and deposit pallets, and they come in two varieties, also counterbalance and stacker type. These are the robots, and also BluePath Robotics is providing centralized software and services to innovate, automate, and integrate AMRs into production lines. The peripheral manager facilities communication with the production floor, and the material flow manager designs and integrates production plans with the AMRs. The fleet manager coordinates all AMRs and peripheral assets based on material flow. All manager applications are accessible via a web user interface with role-based authenticated access. This is the simple topology of the central software system, and all generated messages are stored in a data lake to facilitate the analysis of performance metrics and predictive analytics of the AMRs and the overall operation. Deployment depends on the requirements, and it depends on the class level of deployment. Thank you very much for your attention. Thank you.
Thank you very much for the introduction and invitation to participate in this HiCONNECTS webinar. I will be presenting a life science and health use case in the framework of HiCONNECTS. As I understand, the audience is not familiar in life science and not specialized in cryo-electron microscopy, which is the technique I will be focused on. For that reason, I organized the talk as follows. I will give some basic statements about this life science and health use case, HiCONNECTS and cryo-electron microscopy, or cryo-EM. I will be giving later an introduction to cryo-EM and its impact, finishing with challenges and solutions of this project, talking specifically about cryo-EM software and IT infrastructure. So what is this life science and health use case? We have the following scope: to build a demonstrator for the important application area of life science using HiCONNECTS concepts and outcomes. To realize this scope, we have the following task: to improve a workflow. It's called a cryo-EM SPA workflow for proteomics and virus research to enable faster drug discovery. I will explain you in a minute what is this cryo-EM SPA workflow. But the goal is to enable faster drug discovery. This is a collaborative effort of Novalix, which supplies drug discovery pipelines to other pharmaceutical companies, NVIDIA as technological partner, the Eindhoven University of Technology giving support on computing, and Thermo Fisher Scientific, supplier of instruments and service for science in general, but a leading provider of cryo-EM technologies. Cryo-electron microscopy is a technique of imaging with high resolution. The instrument that we use is a cryotransmission electron microscope, depicted here in this picture schematically. And to go through the key elements of a cryotransmission electron microscope, we can make the comparison with a light microscope. Instead of having light source, you have an electron beam source along with subatomic resolution. Instead of glass lenses, you have electron lenses to control the electron beam, for example, to change magnification. Something specifically for cryotransmission electron microscope is that you are able to maintain the samples at liquid nitrogen temperature that is around minus 180 degrees Celsius. So we are talking here about cryogenic temperatures. And this fill up two purposes. One is to keep the structure of the proteins well preserved. And the second is to maintain the sample in a kind of solid state capable to resist the vacuum inside the electron column of the microscope. Otherwise, a liquid sample will evaporate in a few seconds. And finally, we have a camera. Instead of using your eyes or an optical camera, you have a direct electron detector to capture the subatomic resolution. The camera is located at the bottom of the microscope. Good. Cryo-electron microscopy has gained a crucial role in structural biology in the last decade, basically because it's capable to achieve high resolution. The most popular technique is single particle analysis. And why single particle? Because it is applied to isolated proteins or group of proteins that form stable complexes. The workflow is relatively simple, laborious but simple. You extract and purify your target. You apply 1 drop of the solution to a cryo-EM grid, a metallic grid covered by a plastic support. You need to freeze them very quickly to produce vitrified ice. And then you can transfer this sample to the cryotransmission electron microscope. And not all the grids are suitable for high resolution data acquisition. You need to determine if the sample is suitable, and then we are talking here about screening your sample. This is a time-consuming step, and our efforts in improving the workflow has to do with this step of screening. Once you know that your sample is good enough, then you take images per hours or days to acquire many images. In each of these images, you have many copies of your protein. And this is because the cryo-EM images are very noisy, and you need to average many particles in different orientations to be able to increase the signal-to-noise ratio. Once you have many different views with high contrast of your particles, then you can apply methods to reconstruct a three-dimensional volume. So the final goal is to produce 3D near atomic structure of proteins and macromolecules from vitrified, purified samples. And with these structures, you understand better the protein function. This is the goal of our colleagues in academy. But as it were not enough, this is also very valuable in practical application with strong application in society, because our partners in the pharma industry are telling us that structure-based drug design have 2 times the rate of clinical success at 50% of the preclinical time, and also reduction of cost compared to not having a structure. Okay. So cryo-EM is accelerating the drug discovery with rational design. Why is that? Because when you have the high resolution structure of your target molecules, you can design better the drugs and the carriers. You have information exactly of the atoms surrounding your drug. So to have this high resolution information helps pharma to design more effective drugs and vaccine by knowing exactly how they interact with their targets. It also helps to produce safer therapies because you will have specific information about the carriers of the drugs, for example, as in this image with these nanoparticles. They are used in RNA vaccines and gene therapy delivery systems. And something that is very interesting is that it has a broader impact. You are not constrict to only one particular disease. Cryo-EM supported development of treatments for cancer, infectious diseases, or rare genetic disorders. Here are some examples of these structures. Receptor that binds small molecules inside, a membrane protein with antibodies bound to it, or a viral protein also with antibodies that helps in vaccine research. To visualize the impact, the big impact of cryo-EM in this rational drug design, it's better to see this graphic here. In 40 years of research using the alternative technology to produce high resolution structure, that is X-ray crystallography, the number of drugs approved were very limited. And only in the recent years is when this number of drugs in clinical trials or approved has significantly increased, and they are using cryo-electron microscopy. So as I mentioned, there are plenty of areas in which cryo-EM is helping to a better drug design, for example, in oncology, neurological or neurodegenerative diseases, infection diseases like vaccines, antivirals or antimicrobials, and rare diseases. Here are some examples here from these drugs approved. One can you recognize easily is the COVID vaccine. So we complete the slide that I presented you before. Now you understand that our task is to improve this cryo-EM SPA workflow, The motivation is that this cryo-EM workflow produces large data sets, needs to be processed in an efficient, integrated, and transparent way using various compute and storage resources efficiently and dynamically. The goal is to speed up data transfer, storage, and processing by using innovative hybrid chips and concepts developed in technical scope of HiCONNECTS project. Let's talk about the challenges and solutions in the cryo-EM workflow. The workflow has challenges in every step, starting by the gene coding for a protein, protein expression in model system, and protein purification. But our colleagues and Novalics have plenty of experience on that field and are capable to produce highly purified complexes. However, not all this material is suitable for cryo-EM, and you need to go through a process of sample optimization that relies on at least some imaging at the cryo-electron microscope. Our company is providing tools for that, starting with sample optimization kits, the vitrification machines, and the cryo-electron microscope, coupled to a specific software that we call a smart EPU for taking in a very automated way these images. And if your protein is good enough, then you get high quality images that you need to process to build your models. However, the story doesn't end here. You want to repeat this for many grids, many different proteins and compounds, and quickly you will face another challenge in data transfer and data management. And our colleagues at NVIDIA and also Novalics are working in these areas. So I will be focused on the Smart EPU next and give you some ideas about the data management challenge later. A Smart EPU is a bundle of software with the core being EPU software. That is our automated data acquisition software. It's very popular because it's very easy to use. You have tabs that organize the task in a very organized manner, logical manner. And a user can set up data acquisition sessions for one grid in less than 30 minutes. To illustrate this procedure or the critical steps in this setup, I have this snapshot of the user interface. So here you have a low magnification image of the grid. Is, as I said, a metal grid that is a mesh. So here in black, that has squares. This the whole grid is covered by a plastic support that is perforated with holes. You can see the holes only if you take an intermediate magnification image of one of these squares. And then inside these holes is when you have a very thin layer of ice where your protein is embedded. You can see the protein when you take a high magnification image. So the setup of a EPU session consists in select the grid squares that are the best ones and the best foil holes that are very thin enough or that contain ice thin enough to give you the best contrast of particles at high magnification. And this is normally a procedure that requires some expertise and takes some time. And that is the reason why we have been working in the automation of these steps. And now we are talking about a smart EPU that has additionally AI algorithms to overtake these activities that normally a trained user will do. So we have developed trained neural networks, for developing the tools for automatic selection of grid squares, the identification of the foil holes, and the selection of foil holes based on eye thickness. The other part of the workflow in EPU that is taking images at low magnification and acquiring the high magnification images are already automated since a long time. But these were the manual steps that now do not require any pre-knowledge from the users. So we are getting high quality because we are focused on the best places to take images, increase efficiency, less time to set up session because it will run automatically, and is promote easy adoption. You don't need expertise for that. To even facilitate further the usage of these AI algorithms, we have bundled them in what we call a smart screening. I will run here the movie in which you say that you see that with an easy setup, you need to specify the number of squares, the number of foil holes per square, and the range of eye thickness that you want. And then with this setup, you can start your session that will run independently without user supervision. The sequence starts with the automatic acquisition of several low magnification images to cover the whole grid. Then the program identifies the best squares, goes there, take images of these squares, and classify and identify the foil holes to take high magnification images in each, in representative holes to get an idea of the variability of ice quality in your grids. So the execution proceeds completely unattended, and the result will be a set of images of high resolution in which you can see if your protein is concentrated enough and if it's not fall apart, and identify which are the conditions of ice that are the best for your protein. So this gives you an idea of how we are accelerating the setup of a session and via software. And now I want to talk about the data management challenges. This automated image acquisition imposes high demand of data management. The state of the art at the moment is with our most recent model of cryo-electron microscopy and the best camera, you can get up to 1,400 images per hour. This translates in about 340 gigabytes per hour. And you can imagine that a microscope server that we provide with 70 terabytes of storage will be full in only a few days. We need to deal with a production of 1 or 2 petabytes of data per year, raw data storage. And as I said, this is the current state, and with all the improvement that we are seeing in the field, we expect even higher data volume. So cryo-EM generates terabyte scale data sets requiring large data storage and compute. This imposes network demands. Terabytes of data needs to be transferred from different locations. We have the wish of a real-time processing because the online analysis enable quicker results, but also feedback on sample preparation, and you can make improvements if needed if you have this real-time processing. There is additional requirement for fast computing in post-acquisition processing to keep up with project timelines, and the infrastructure should be robust enough to be able to manage data from a microscope that in principle is running close to 24/7. Good. Say that, I will try to summarize what we have discussed in this talk with this slide. incorporating some new elements. So here I talk about the challenges that we are facing in cryo-EM workflow. Some challenges refers to sample optimization that are related with hardware and software development. In this interaction, Novalics and Thermo Fisher are critical here. NVIDIA not only provides the GPUs that we are using to deploy our solution of AI, but also actively developing heterogeneous integrated co-packaged optics transceivers. This has to do with data transfer, and Novalics, in collaboration also with NVIDIA, is working on develop a data management and processing pipeline to keep data organized and flowing in different sites. So sample optimization, hardware and software development, high-speed infrastructure, and new technologies for data transfer are some of the aspects that we are covering. And through the combination of all partner efforts, we predict a possible speed up of the workflow up to a factor of 4. With that, I want to acknowledge all the participants in this project, the supporting agencies, and you for your attention. Thank you very much.
Welcome to HiCONNECTS, Heterogeneous Integration in Action, powering the next era of connectivity webinar. Thanks for joining us. Now, let me introduce my session. My name is Tolga Bodurlu, and I work as a lead software and functions ADAS AD engineer at AVL Turkey. And today, my topic is about connected and autonomous mobility. And now, I will give you today's roadmap in here. I will start with a quick introduction to our objectives, then I walk through our autonomous driving software architecture and the explainability layers. After that, we will look at the VTX connectivity and test scenarios. Then I will mention about the conclusion and brief feature works. Now, I will go with the introduction part.
Actually, our objective is develop connected and autonomous vehicle software with a strong emphasis and transport on the explainability for our AVL Turkey's autonomous driving system. And actually, this work is hardware support from HiCONNECTS partners, which are NXP on radar side, ULAG on VTEC side, and Billinator on the interpreter side. And also internally, we contribute the core software for the XAI planner, XAI interpreter, and VTEX integration. And I will talk about the general features and also hardware provided by our partners in the following slide. And NXP actually developed a heterogeneously integrated automotive radar platform, which actually gives us a clean, high-quality data. And this high-quality data actually helps our perception work better and also faster. We will actually measure results with a simple KPIs like range, speed, angle, and also latency. And also use them in our sensor fusion algorithm. And for the NXP radar integration can be done like that way. This NXP radar gives us a feature and object list, and actually we obtain a word model using that object list, then give this object list result to our XR interpreter and also XR planner algorithms. And the better input means that actually we create a more clear decisions and also more easier explanations. And we will test this radar on our track, compare with our perception algorithms, and pick that what will be works best in our solution. And in the following slide, I will talk about this ULAX V2X modem. This ULAX V2X modem actually connects vehicles and also roadside units, and it supports 5G, LTE, Wi-Fi, and also GNSS, and also working on the embedded Linux. And this ULAC modem for the integration phase, the modem has two antennas for VTX, GNSS, and Wi-Fi, Bluetooth, and also Ethernet port. And for this modem, it supports also GPS, GLONASS, Beidou, and also Galileo with a high accuracy. 1.5 meter accuracy. And actually, this is our hardware side of our system. And now I will continue with my general structure of our algorithms. And our actually architectures follows a V-shaped layered, which includes XI part. Actually, it also operational, tactical, and strategical levels. By the way, the XI means that the explainable artificial intelligence and the perception and also connectivity layers fit these decision tasks. And the XI layer actually captures the why a decision is made and explain this decision at the end of the result. And the XI interpreter and also XI planner layer structure that will provide the explanations related with each driving action to user. And these explanations can be expressed to the user in textual, voice, and visual formats. So the engineers, safety operators, and end users can all understand system behavior at the right level of detail. And here is a big picture of our HiCONNECTS projects. Actually, we take inputs from NXP radar and from V2X messages from ULAC modem, and our XI interpreter and XI planner algorithms get this input and creates our results. Then shows our HMI to these explanations online, so people can see and trust the system and review a decision later. And for the following slides, I will mention about this XI interpreter and also XI planner algorithms in briefly. And now I will go with the XI interpreter part. So actually, the initial of this presentation is why this XI interpreter is needed. Actually, in today's deep networks can feel like a black boxes, and in autonomous driving, actually that's not too much okay, because we need to see what drove each choice. And for that, we use two complementary methods for the interpreter part. First one is learned attention weights. It actually provides the visual evidence, and the second one is object level attention. It actually it's the agent influence and give the signal context. This combined two methods explanation keeps the planner focus and makes the HMI outputs easy to trust. And also for the XI interpreter, we also working with the validator, because we actually collaborate with the validator with their social AI algorithm, and we fuse these two algorithms to make attention more accurate before gives the result to the XI planner part. So we combine these learned attention ways, object level attention with the validator social AI to create a more stable and transformative explanations. And this is actually a collaboration with the validator for the interpreter part. And as I said before in the two slides, XI interpreter employs two complementary method. One of them is object level attention. The other one is learned attention weights. So the object level attention actually ranks cars in our lane and next lane by impact. And in this algorithm, it uses the speed, distance, and orientation of the other vehicles. And so each object actually gets a score from 0 to 1. You can see on the right-hand side, right upper side, and also below the right below side. Each of the object gets 1 to 0. Y is highly influential. 0 means negligible. And these scores actually informs the explanation and also makes more clear decision for our algorithms. And it shows the most critical object near the autonomous vehicle. And this object level attention demo shows us the result of that. And for the other structure, learned attention weights, we use a GradCam for in our algorithms, and it gives an attention map which shows where the model focus for each prediction. And for the learned attention weights, we can see the results of the learned attention weight algorithms in this slide. When we look at this slide, we can say that in practically ResNet algorithms produce the most reliable and explainable attention maps. So the accuracy and also interpretability matter. ResNet is better than the MobileNet, but MobileNet is also real-time friendly. And if you have a weaker hardware or you might use this MobileNet also, but for the accuracy and interpretability matter, you can use the ResNet algorithm version. And also for the this slide, it actually shows the trade-off between this ResNet and also MobileNet. You can see that, as I said in the previous slide, the ResNet confidence scores and also prediction rates much better than the MobileNet. But on the other hand, MobileNet performs much faster and also ran quickly on the low hardware devices. But in the real-time scenario, and accuracy and attention is more important to us, we can go with the ResNet models in our system. So this is the performance comparison for the GradCam. So in the next slides, I will present the section related to the XI planner part. And I will begin with the why this XI planner is needed, because as I said in the XI interpreter part, also the planning decisions must be transparent, and we need to create a more transparent and more reliable result. So we create a hierarchical reinforcement learning setup. A high-level agent selects behaviors and low-level controllers execute them. We do not directly control the low-level part. We only train the high-level agents, and high-level agents select the behaviors, then low-level controllers execute them. And these training algorithms, we use a custom Carla environment to create our own algorithms. And as I said before, we create a actually the planner can explain this sentence. Actually, for example, I slowed here because this curve radius decreases and my target velocity will exceed a lateral comfort limits. The XL planner actually sent this result, and for that we train our algorithms to keep our ego vehicle more robust and more safely operations, and also more transparent operations. The pipeline actually we see the XI interpreter results and take them as an input and use this input and create our planner algorithms. Then we send our result to the controlling part and the ego vehicle controlling that in that way. So in the XR planner part, we have two examples in here. One of them is velocity adjustment. The other part is lane change example. And the first one, velocity adjustment, actually this velocity agent tracks the reference speed without overshooting, decelerates before entering curves, and maximize speed safely according to curvature. And for that, as I said before, we use Carla environment. We create a Carla demonstration in here. The high level agents picks the driving mode, the low level agents anticipate the curvature and reduce speed. For that, for example, in that demo, the reference speed is 79.2 kilometer per hour, and our autonomous vehicle speed is setting 77 kilometer per hour. And for example, if we increase the reference speed in the common 1 or 2 seconds, when we increase the reference speed, the agent learns that and increase the autonomous vehicle speed as well. And we train this agent in the Carla environment for different kind of map. And currently, we are also currently developing in our algorithm in that way. And as I said, we have two examples. The other part is lane change, and this for the lateral maneuvers, policies are trained on curves, trails, and also mixed traffic. Actually, the planner anticipates upcoming curvature, respects the reference speed, and also perform safe explainable lane changes. And for that, we have also in real time and also Carla demo. But in the real time, we only see the if the lane change maneuvers is performing when we set the lane change is okay. The vehicle successfully executed by the lane change maneuver, confirming that the planner decision logic translate into the physical test. We only show in this environment, and this is our non-traffic environment. And we actually, for the HiCONNECTS project, in the final part, we use a demonstration in here, and I will also mention that in the V2X demonstration part. And for the lane change, we have also Carla simulation demo in here. And for that, create more scenarios for lane changing algorithm in the Carla environment, because there are we add more traffic and more extreme scenarios in the Carla. We use the lane change simulation algorithm in here. We will also develop this algorithm, and next couple of months we will try to finish this lane change algorithm as well. Our developments are continuing right now. And these are the XR planner part, actually. And in the following slides, I will present the parts related with the V2X. And actually, this is the system architecture for the V2X part. On the left side, we have a connected autonomous vehicle and also connected autonomous modem. And in our autonomous vehicle, we run our stack on ROS, and data from V2X modem 1 comes over Ethernet, and we send using this ULAC V2X modem to the connected vehicle. And the right hand side in the connected vehicle, and in this demonstration, vehicle speed read from OBD2 port and goes to a Raspberry Pi. Then Raspberry Pi communicates with the ULAC modem with using a common protocol with TCP IP connection. And also this Raspberry Pi feeds to the ULAC modem for the negotiation results, and also left and right turn state. And this negotiation actually is simple. For the connected vehicle, share its intent. The connected autonomous vehicle evaluates and it replies with using this to ULAC V2X modem and communicate with each other. Then when the connected autonomous vehicle replies, the HMI then shows green, orange, or red. So the connected vehicle driver proceed in a safe and coordinated way. So this is actually a basic system architecture for the V2X case. And for the more detail, the data collected from connected vehicle through ELM and using OBD port, then conversion this data from into the CAN frame and do the communication between Raspberry Pi and the modem with using the TCP/IP protocol, and also the HMI shows the negotiation result with the red, orange, and green. And according to this negotiation result, the connected vehicle drives that way. So this makes more safely operation in the connection environment. And this is actually our test case, as I said before, 2 or 3 slides earlier. This is the test environment. And for the V2X connectivity test scenarios, we have on real test scenario and also again Carla environment. For the real test scenario, a connected vehicle and also a connected autonomous vehicle approach and intersection in here. And the driver in the connected vehicle selects the turn signal, and so this intent is sent to the connected autonomous vehicle via V2X modem. Then the connected autonomous vehicle takes this result and operates, then replies to the connected vehicle again. And according to this HMI result, the connected vehicle guide to safe coordinated crossing. And for the second case scenario, actually this is more complex cases. The non-connected vehicle partially blocks the connected autonomous vehicle perception. So the connected vehicles broadcast, for example, a left lane change intent. So the connected autonomous vehicle uses that intent to plan the right lane change and creating a safe coordinated maneuver. So this actually shows us how intent sharing reduces ambiguity and also improves safety for lane changing and also other stuff as well. Actually, this is by end of the presentation, and also I will share the general results and also future plans. Through the HiCONNECTS, we enabled real hardware, software, and also software co-development with NXP radar and the ULAC modem integrated our stack, and also interpreter collaboration with the Brunnator site. We strengthened our perception and also planning algorithm and also end-to-end explainability. And we created a new simulation environments. So we actually do a test using this environment, and also we have produced some publications, and based on this open source Scala environment, we created our own simulation, open source simulation environment. And for the next phase, we will complete on real vehicle tests with our radar and also our modem, and publish the KPI benchmarks versus our targets, and also get these KPI results and see the consistency between evidence and also influence. And for the V2X, we will extend the real time demo for the intersection for connected vehicle and connected autonomous vehicle, and we will standardize this safety and testing environment. And this is actually end of my presentation. Thank you for listening, and sorry for the technical issues for the presentation.
Well, thank you very much, Tolga,
You're welcome.
Giulio, Hussein, and Daniele. Now we start with the question and answer session. So please, let's go ahead.
Okay, Daniele speaking. I see a question for me regarding the structure and the sample that we used in order to correlate inline parameter with electrical wafer sort. Consider that in this project we take the status as is. So for different product we have a process control plan, and for each process step we have some rule from statistical point of view that take in account needs for product and also for the machine that we use for the process. So usually we sample at least 3 wafer with different site, and typically we don't talk in this case regarding defectivity, but more dopant thickness and CD, for example, overlay. So the assumption that we put at the beginning was that is possible in principle to consider this sample as a representative for the lots. For sure is not always true, because sometimes we have 1, 2 wafer that have a different performance. Also for this reason, in the second step of activity, our partner Siemens EDA and MIT introduce also fault detection data. In this way, it's possible to reduce the approximation. So we don't talk only regarding an average performance for lot, but we have the opportunity to go down at the wafer level. I hope to have answered to the question.
Thank you, Daniela. So the next question I will put to Julio. So Julio, how do you train your networks, and how does it compare to an experienced user?
Okay, thank you for the question. Yeah, we have a set of data sets that we have acquired and let expert evaluate those data sets. We got, for example, many different squares, okay? And there are objective criteria like the apparent size, but there are also subjective, and that is why we use the expertise of several application experts that assign a score based on different qualities for these particular squares. For example, the degree of contamination, ice contamination, there are blocks of black boxes in the images. The texture that correspond to protein aggregation, how broken the plastic foil is. So there are several criteria, and then we weight those scores and combine them into just one quality assessment. And about how does it compares with the customer, with persons, we have evaluated, and actually when you have, for example, a grid that is perfect and all the squares in an image looks very nice, and there is no correlation because it doesn't matter which square do you select. But when you have a gradient, that is the most typical case, there are good and bad squares, then there is a very, very good correlation. So the best selected squares by the AI are very close or are the same as the best that an expert user will choose. So thank you for the question.
Thank you so much, Julio. So we welcome any questions that you have for our speakers. Still, there's a little bit of time left. Maybe I can give it 1 more minute. I think there's quite a few of you still here, but otherwise, all I can say is that, the presentations were incredibly informative from Hussein, Tolga, Daniela, and Julio. I think we will be sharing this, of course, on our YouTube channel and you'll be receiving the link for it. Well, thank you again so much for joining, everybody. And please stay in touch on our social media channels, or you can catch us on HiCONNECTS.org. Thank you so much. This has been a very informative session. Thank you.